Hi there, welcome back. We've been talking a bit about probability. We're going to continue talking about probability, but we'd like to know what's the probability of two things happening simultaneously? The probability of A and B at the same time. This kind of probability statement is called a joint probability. And to answer such questions, we're going to have to develop a rule for calculating it, a formula. That formula is called the multiplication rule. It's not that hard. You're really just multiplying two numbers. Now, which two numbers you multiply, that maybe could get a little tricky, but not terribly. Probability of x and y happening at the same time or together really depends on whether the probability of x and y, whether those two things depend on each other or not. See, if x and y are independent of each other, like you've got a coin flip and the roll of a dice. These are two independent events. Then you can calculate the probability of a heads and a 6 just by multiplying their two probabilities. But sometimes x and y are not independent of each other. Sometimes the probability of y depends on the outcome of x. And so then you would need to make an adjustment and revise your probability once you know what happened with x. So that's kind of the game plan. We're going to be multiplying two probabilities to get at a joint probability. As a reminder, two events, A and B, are independent if the outcome of A doesn't affect the probability of B happening at all. Classic example, two coin tosses, right? Or three coin tosses, or four, right? I don't know whether the coin is fair or not, right? We've got one coin. Now, if I flip it 5 times and it comes up heads, what's the probability that it'll come up heads a 6th time? Now, I'm not sure. Maybe it's not a fair coin, but the coin hasn't changed. So the probability that it comes up heads a 6th time is going to be the same probability that it had come up heads a 5th time, or the 4th time, or the 3rd time. All of these are independent flips. Now, the coin could be biased. I'm not disputing that. But it's not like the probability changes on you. The coin is the same coin. It didn't warp when you flipped it or something. It's not like you can change physics. So the first multiplication rule is the simple version. It's the one that applies when A and B, these two events, are independent of each other. The formula is really straightforward. If you want to know the probability of A and B happening, then all you need to do is multiply the probability of A times the probability of B. It's very straightforward. So let's go back to that coin flip and die toss example. What's the probability that you get a heads and a 6? Well, that's just going to be the probability of a heads times the probability of a 6. Now, what's the probability of a heads? Let's just presume that it's a fair coin, so it's 50-50, it's 1/2. And the probability of a 6, let's presume the dice is also a fair dice, so the probability of any one particular face coming up is 1 out of 6. Oops, and that's multiply. So what's the joint probability? It's just going to be 1 out of 12. It's really straightforward. What's the probability that we would have 6 heads in a row? Like we just flip 6 coins, or the same one coin 6 times. What's the probability of 6 heads? Well, each of these flips is independent. So the probability of 6 heads is the probability of the first head times the probability of the second head times the probability of the third times all the way down, right? There are 6 of these. So if it's a fair coin, the probability would be 1/2 raised to the 6th, or 1/2 to the 6th, which is, if I remember correctly, about 1.5%. Yeah, about 1.6%. Right? So the rule is fairly straightforward, at least when A and B, these two things, or these 6 things, are independent of each other. What if they're not? If A and B are dependent on each other, then we need to adjust the probabilities that we're using. So if I want to know what's the probability of A and B happening, then it's the probability of A, but now the outcome of A changes the probability of B, right? That's what it means to be dependent. So I'm still multiplying probability of A times the probability of B, but now it's a revised probability. I need to adjust the probability of A to express the fact that now it's conditional on A already happening. So revise the probability of B conditional on the fact that A already happened. Now, since the probability of A and B is the same thing as the probability of B and A, right, these two things are equal to each other, then I can just rewrite this entire formula by flipping the order of A and B, and I would get the probability of B times the probability of A conditional on B, this revised probability of A. And so these two things are going to be equal to each other, these right-hand sides. It's going to turn out that we can use this to derive yet another rule in statistics called Bayes' rule. But I'm getting ahead of myself. Let's keep working on the multiplication rule and joint probabilities. Okay, so we saw how to calculate probabilities for two coin flips. What about two pulls from a deck of cards? Well, if I'm not putting the first pull back in the deck, then my probabilities do change. So what's the probability that I would draw an ace on the first draw and on the second draw? And I'm not putting that first card back in. Well, the normal probability rule would say what's the probability of A on the first, ace on the first, times the probability of ace on the second, but now we need to adjust that second probability. Okay. Now the probability of an ace on the first draw, there are 4 aces in a deck of 52 cards, so 4 out of 52. But once we've pulled that ace, then we need to revise our probability for the second ace. Now there's only 3 aces left out of 51 cards. So we have to multiply by 3 out of 51, not 4 out of 52. When we multiply these two numbers, we get about 4.5%. Okay, still multiplying two things, but that second thing is a revised probability. Okay, so here's a simple Lotto type question. Let's say that there are 52 numbers. I picked that number for a reason. It's supposed to remind you of the last example. But you've got this scratch-off sheet, this giant scratch-off sheet with a bunch of numbers. There's 52 of them. And you have to bubble in. Let's say, you pick 1, 2, 3, and you pick 4 and 5. Oops. You bubbled in 4 and 5 out of all of these 52 options. Now, if you pick the right two numbers, you win the lotto. What are the chances of that? Now, this is a simple lotto, but it's kind of like a Powerball. So, well, what is the probability that I would have picked the first number correctly? Well, it's going to be 1 out of 52. But what's the probability that now that I've done this, that I would also pick this second number? Well, I'm still picking 1, but now I'm picking out of 51 remaining because I can't pick the same number twice. So the probability of picking 2 numbers out of 52 correctly are 1 over 52 times 51. Yeah, not bad, huh? Kind of fun. So how should we think about joint probabilities and conditional probabilities? It'd be nice to have some kind of visual reference. Well, we can go back to this idea of a sample space, of probability as a fraction of a set of outcomes. Let's have the whole set of outcomes be this blue box. And if I want to know what's the probability of A, then I just need to know what fraction of that blue box is A here. Right? That's how we use that graph. But now I want to know what's the probability of A conditional on B. What is this updated probability? Well, if I know that B has happened, then my sample space is now the set of all possible outcomes where B happens. So my revised sample space, once B has happened, is this circle right here. So if I want to know what's the probability that of A, now that I know that B happened, right, well, I can only look inside this circle. The only place that A happens is here, where A and B happened. Okay, so in math then, what's the probability that A happens given that I'm restricting my sample space to B? Okay, then it's going to be the probability of A and B, so it's going to be this area right here, as a fraction of this B circle. So divided by, as a percentage of B, right? You want A and B as a fraction of this entire restricted output or probability space. So the rule is clear, right? It's the probability of A given B is equal to the joint probability divided by this marginal. And think of this up and down slash, this conditional slash, as though it were a division sign. You'd be dividing by B. That's how I remember to put B in the denominator there. So that's how to calculate the conditional probability if you know the joint and the marginal. But you can just re-express this, this formula by cross-multiplying both sides by the probability of B. And this B cancels on the right. And we have our multiplication rule number 2. Okay, so these two equations are identical. You've got 3 potential unknowns, x, y, and z. And if you know x and y, you can figure out z. Or if you know x and z, you can figure out y, or vice versa. So let's practice doing some of this. And we'll go way back to the idea of probability as counting. So here's, I hope, a fun example. We've got, you're at a bar. And let's just suppose that you know, somehow, that there are 20 single guys, 42 taken guys, 22 single girls, and 38 not single girls in the bar. Usually you don't know that, but let's just pretend that we know that for the sake of this example. Then can we calculate probabilities out of these frequencies? Yeah, of course. So first, let's fill in some blanks here. Like, we might want to know what's the male-female ratio in this bar. Right? So if I don't care whether the guys are single or not single, how many guys do we have? I just add up 42 and 20, and I get 62. And how many girls do we have? We just add up the 22 single girls and the 38 taken ones, and we get 60. And so how many people do we have at the bar? It's got to be 122. Now what about, like, how many single folks do we have? 42. And then adding up the 42 and the 38, we get 80. Right, the 42 plus the 38. And if we add up 42 and 80, we get 122 as well. So that's how, like, we double check that I know I did my math right. Now, let's take these frequencies, or counts, and see if I can map that over into probabilities. In other words, let's say you just bumped into somebody randomly. You're backing up, and you bump into somebody. You want to know, is it a single girl? You might want to know that. So let's say we want to figure this cell out. All right, so we know there's 22 single girls in the bar out of 122. So 22 out of 122. That's 18%, 0.180. How many single men do we have as a percentage? Well, that would be 20 people, these guys here, out of 122, which is 0.164, or 16.4%. How about taken men, not single men? Well, that would be 42 out of 122. Which is 34.4%. And this other probability is 38 out of 122, which is 31.1%. Okay, so maybe we want to know what percent of the bar is guys. All right, so we could do this two different ways now. We know that it's 62 out of 122. So that's one way of doing this. We could do that and get 51%. Or we could just add up 164 plus 0.344 and get your 51% with rounding error. How many women do we have at the bar? Well, we could add up 18% and 31.1%. We could use the rule of complements, for example. So if I know that 51% of the bar is guys, then it has to be the case that 49% of the bar is girls. What percent of the bar is single? It's 42 people out of 122. We could do that. Or we could add up 0.164 plus 0.180 to get 0.344, 34.4%. Likewise, if we add this 34.4, different 34.4s, if we add this 34 right here, oops, and this 31, we get 0.655, 65.5%. And if we add up these two numbers, we will get 100%, which is also another double check that we did our math correctly. Okay, so we've just figured out joint probabilities and marginal probabilities. Marginal probabilities are these guys that we calculated in the margins of this table. Margins is just statistical fancy speak for not conditional. So it's just probability, or like unconditional probability, or if you really want to be fancy, you bust out the word marginal. And it sounds like, oh, this guy took a statistics class. Okay, so what I've done in this table is I just recopied all the stuff that we'd calculated, all these joint probabilities, just so that the table isn't all scribble scratchy. And we're going to use this information to calculate conditional probabilities. For example, you're at that bar, you're backing up, bump into somebody, it's a girl. You want to know, is she single or not? Right? So you want to know what's the probability of single given that you're talking to a girl. So you can ignore the probabilities of singleness associated with the guys and restrict your sample space, restrict your attention to the probabilities associated with girls. So what's the probability that this girl you bumped into is single? So we can use our conditional probabilities that we get from our multiplication rule. We get the probability of single and girl divided by the probability of whether we're just talking to a girl, this marginal probability. Remember, we're going to be dividing through by what's underneath this division symbol, right? When you think of that conditional as a division. So what's the joint probability of single and girl? That's 18%. What's the probability of girl? We go to the margins, that's 0.49. So 18% divided by 49% is approximately 37%. I don't know what you think about those odds, but that's what you're facing at this bar. Now, what's the probability that the girl you bumped into is not single? Okay, well, there's two ways that we can do this. First, we've restricted our sample space in both cases to where we only care about the girls. So if I know that 37% of them are single, then 63% of them have to be not single, right? We could use the rule of complements to get 63%. But let's use this conditional probability stuff. So we want to know here the probability of not single and girl divided by the probability that you're talking to a girl. So not single and girl, that's 0.311 divided by the probability that you're talking to a girl, which was our 49%. And this does indeed come out to 63%. Okay, so let's just say that you don't care about the girls and that you want to know about the guy you just bumped into. All right, well, the math is the same. I've gotten rid of the clutter. I've reproduced the table. I've added some decimals there. But let's work out the math. You want to know if this guy you bumped into is single or not single. So we want to know the conditional probability. That is equal to the joint probability, so single and guy, divided by, right, so we think of this as a division sign for a sec, the probability of a guy. So single guys, the joint probability is 0.164. And the probability of a guy, that's 0.508. So 0.164 divided by 0.508 is approximately 32%. Now, what's the probability that that guy you bumped into is not single? It's the joint probability of not single and a guy divided again by the probability of a guy. So not single guy, that's 0.344 divided by this restricted sample space of 508. That comes out to 68%. And we can verify that. We know from our rule of complements that 68 and the 32 better add up to 100%. So there you go. We've just worked through a whole bunch of conditional probabilities. If I had to summarize everything, it would be this. The probability of A and B is equal to the probability of A given B times the probability of B, right? So you might know these two probabilities and you got to figure out the joint. You might know the joint and the marginal, you got to figure out the conditional. It's always where you know two out of these three things and you got to figure out the third thing. So thanks for listening. That's all we got for now. Bye-bye.